Okay, hello and welcome back. In this video we're covering section 9.2. So we're continuing our exploration of the polar coordinate system, and this time we're going to focus on what polar equations will look like and produce some graphs using the polar system. So let's review some of those conversions between rectangular and polar systems. Remember when we are producing a point in the polar coordinate system, it's described as an r value, so like a radius, and an angle. And this is in relation to the pole, which which exists at the origin in the xy rectangular system. And we could still call this point 0, 0. So the distance from the pole to the point, that's our r. And then the angle from the polar axis, which in the Cartesian system was the x-axis, we can still view it in that way, is our angle theta. But if we were describing this as a rectangular coordinate, this would be our x distance and this would be our y distance. So we get this xy-r triangle. And so we can get a few of our translation tools from this. Via the Pythagorean theorem, we can say that r squared should equal x squared plus y squared. We saw last time, if you take the sine and cosine of theta and rearrange the statement a little bit, we get that x is equal to r times the cosine of theta, and y is equal to r times the sine of theta. And then we can also say the tangent of theta is equal to y over x. So we can use all of these to translate between rectangular and polar equations and coordinates. So let's go through a few examples using this. So the first one, and this is in polar form, is that r equals 3. So there's no theta in the equation, which means it's essentially a free variable. It can take on any value. So it's worth trying to think before we work on this, just what you expect this to look like. Something where the radius is always equal to 3, or the distance from the origin or from the pole is always equal to 3. You might be able to already expect what this will look like. And so for converting between an equation in polar and rectangular coordinates, there's a few strategies. Sometimes we would square both sides, and sometimes we might multiply both sides by r. In this case, let's square both sides of the equation. We would get r squared equals 9. And we're doing that because we can replace r squared with x squared plus y squared. So this would convert to x squared plus y squared equals 9, which you might recognize as a circle centered at the origin with a radius of 3. So the equation of a circle, I wrote a G instead of a Q. The equation of a circle in general looks like x minus h squared plus y minus k squared equals r squared, where the center is the point hk and the radius is r. So what we have here is a circle. 9 is r squared, or the radius squared, so it would have a radius of 3. Centered at the origin. So doing a rough sketch, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. Let's try to make a nice circle. Not great, but close enough. So looking at the original statement, um, it kind of makes sense. It's something where the radius is always 3, or the distance from the pole is always equal to 3. We can imagine going out a distance of 3 units, and then letting theta be free. You just let the angle be anything. And we end up tracing out a circle. It's all collection of points where the r value stays constant. So how about if the angle stays constant, but the radius is free? So this is theta equals pi over 3. So now the radius can change, can be positive or negative, but the angle is always the same. So what would this look like? Well, we can translate it. Since we know that the tangent of theta equals y over x, we can say that the tangent of pi over 3, that's our angle, equals y over x. The tangent of pi over 3 is the square root of 3. So let's solve this for y. We can say that y will equal x times the square root of 3. Or maybe I should put the square root first, and it will look. Hopefully you recognize that as the equation of a line with a slope of the square root of 3. And the y-intercept is 0. So I'll just say this is the square root of 3. Let's just say that this is 1. Probably not totally perfect, but just for the sake of throwing a few points here. Some line with a positive slope. So let's think about what this is saying originally. The angle is always pi over 3, or 60 degrees. So imagine like, yeah, something like that, 60 degrees. And then we're letting the radius be any value. So it could be a positive value or could be a negative value, but the angle always stays the same. So we get this equation of a line. Next we have something slightly more complicated. So we have r times the sine of theta equals 2. But let's remember r sine theta was equal to y from our previous statements. So we can just replace that with y equals 2. This is a horizontal line going through 2 on the y-axis. So the y value is always 2. And we can see the same thing for a vertical line. If we have something like r times the cosine of theta equals negative 3. We said previously r cosine was equal to x. So this translates to x equals 3, or an x equals negative 3. So that'll give us a vertical line going through negative 3 on the x-axis. So the book gives us this theorem. Let a be any real number. Then if we have r sine of theta equals some number a, we have a horizontal line. And if we have r times the cosine of theta equals a, we have the cosine that gives us a vertical line. in number 5, we have r equals 4 times the sine of theta. This time we don't have an r attached to the sine, and we have an r on the other side of the equation. And we're always trying to produce like an r squared or an r sine theta, so it would be nice to have an r on both sides. So that'll be our technique here. Let's multiply both sides by r. So that will give us r squared equals 4r sine theta. And we said r squared we can replace with x squared plus y squared. And the r sine theta we can replace with y. So we have what's starting to look like the equation of a circle, but we have this extra y term. If you remember from our last video, we placed this on the other side and put it into the equation of a circle using completing the square. So if we subtract the 4y to the other side and complete the square on y, so I would take the negative 4 divided by 2 and then square it. So that should give us a positive 4. So that's the number I'm going to add to both sides of the equation. And then that produces something with y that we can factor into a perfect square. Notice this factors into y minus 2 squared. And this will be equal to 4. So this gives us a circle with center 0, positive 2, and radius 2. So the center is up there at positive 2. And it has a radius of 2, so it should go 2 units above and below positive 2. And then to the right, 2 units, to the left also 2 units. So we can see we get the equation of a circle, and if it involves the sine, we should see the circle appear like this above or below the x-axis. Let's see a different version where we have a cosine. But this was our transformed equation, so let's do the same thing with the cosine. So we have r equals negative 2 cosine of theta. We're in a similar situation. We have an r on the left side. It'd be nice to have r squared. And we have cosine on the right side, so it would be nice to have r cosine theta. So let's multiply both sides by r. That will give us r squared equals negative 2r cosine theta. Then we can replace the r squared with x squared plus y squared, and the r cosine theta with x. Then let's move the 2x over, so it'll appear positive on the left side. And then let's complete the square on x. So 2 divided by 2 is 1, 1 squared is 1. So we'll add 1 to both sides. This will factor into x plus 1 squared. So we get our transformed equation, get another equation of a circle. So this is a circle, this time centered at the point -1, 0. It's always like flips in sign. If it's positive in here, it'll show up as a negative in the center point. And the radius will be 1, because the square root of 1 is 1. I need to go out at least to 2. I'll go out to 3. So centered at -1, it has a radius of 1. So it should go a distance of 1 unit above and below that center point. So if we have something like this, it involves the cosine, we should see a circle that appears to the left or to the right of the y-axis. Just some general patterns here. And so they give us a theorem in the text. Where if we have r equals 2 times the sine, or basically r equals something times the sine or something times the cosine, we end up with the equation of a circle. And for sine, it'll appear above and below the x-axis, and for cosine, it'll appear to the left or to the right of the y-axis. And that's what we saw with cosine for this one and with sine for this one. So this was converting from polar into rectangular coordinates and then using that familiar equation of a circle, or we saw the equation of lines, something we could recognize in rectangular coordinates. But with polar coordinates, we can also graph more interesting shapes that have less of like an analog in the rectangular system. There's a note in the textbook in the second part about testing polar equations for symmetry that can become very useful because it can make the graphing process a lot easier. If we know that a graph is going to be symmetric with respect to, say, the x-axis, then whatever is plotted up on the top, we know would also appear below. It'll be symmetric. Same if it was symmetric across the y-axis. If we get some kind of curved shape, we can expect the same curve to happen on the other side. Or we could also have symmetry across the origin. So there's a few tests that we can do. If something is symmetric with respect to the x-axis, which we would call the polar axis in polar coordinates, and remember in polar coordinates, it has some radius and some angle, so we'll be dealing with angles. For something to be symmetric across the x-axis or the polar axis, you get the same value if you have some positive theta or some negative theta, some positive or negative angle. So think about like points on the unit circle when we were looking at the cosine. It had the same value for the positive and negative angle. So it's that same kind of idea. So that's the test for polar axis symmetry. It says to replace theta with negative theta, and if you get an equivalent equation, then it's symmetric. To test symmetry across the y-axis, which is the line theta equals pi over 2 in polar coordinates, well, to be symmetric across the y-axis, let's say this is theta, this other angle on the other side would be pi minus theta. So it would produce the same point. If it does produce the same value, then it would be symmetric. So that should remind you of the sine function on the unit circle. The y-coordinate points were the same for a point in the first quadrant and a related point in the second quadrant. And you can describe that angle as pi minus theta. So when you plug that in, so replace theta with pi minus theta. If we get an equivalent equation, then it's symmetric across the y-axis. And to be symmetric with respect to the origin, or we would call that the pole in polar coordinates, basically meaning it's symmetric across the x and or across the y and the x-axis at the same time. There's two ways we can do that. Two different tests. You can either replace r with negative r or theta with theta plus pi. Because if you have some angle here and you add 180 degrees, you would be across the pole or across the origin. So if you get the same value, then, or the same equation, then we would have symmetry there. So let's see some examples, and this will make hopefully a little more sense. So we're going to graph these equations by plotting points and taking advantage of symmetry. So we'll usually start with first testing for symmetry and then thinking about what input values we should do and then plotting from there. It's kind of something messed up in the transfer here. This should be 1 minus sine theta. So that's our first equation. I'll write it a little bit bigger here. R equals 1 minus the sine of theta. So this is different from our circle equations where we just had something like r equals some value times the sine of theta. We have an addition or subtraction here, so that will cause things to look a little bit different. So let's test for symmetry. Let's test for polar symmetry, which is the x-axis. Or let's see how they said it specifically. The polar axis, that's what I should say. So this was the x-axis. So we're starting with r equals 1 minus sine of theta. And the test here is to replace theta with negative theta. And basically we need to see if this negative will not affect the graph. So this should make you think of even-odd identities for the sine and cosine. If you remember for the sine, we were able to pull out the negative and it appears in the front of the sine. So it produces a negative. That will make this 1 plus the sine of theta. So we don't get our original equation back. We want 1 minus sine theta. So we would say not symmetric, no symmetry, at least across the x-axis. Okay, what about y-axis symmetry? I'm just going to call this x and y just to keep with what we've seen before. But this is technically, in terms of polar equations, symmetric about pi over 2. Well, the way to do that was to technically replace theta with pi minus theta. Well, we're dealing with the sine, so we should already know that the sine is going to be symmetric across the y-axis. But we can show this more analytically by using some of our more recent identities. Notice this is a subtraction of angles within a sine function. So if we want to, we can actually just expand this out using angle subtraction for the sine. So if you remember, this should be the sine of the first angle times the cosine of the second angle minus the cosine of the first angle times the sine of the second angle. The sine of pi is 0, so that will make that first term 0. The cosine of pi is negative 1, and then times the sine of theta. So notice this is 1 minus positive sine of theta because of the double negatives. So we get just 1 minus sine of theta, which is our original equation. So we should expect to see some symmetry across the y-axis, which we can also just see what we're dealing with. We're dealing with the sine. Yeah, this will be, it'll produce the same values if we replace theta with pi minus theta. But you can always take the more analytical approach and use the angle addition and subtraction identities. For being symmetric across the pole, or we can say origin symmetry, we replace theta with theta plus pi. And we should already expect, we're dealing with the sine. The sine will have opposite values across the unit circle. Like it's positive in the first quadrant, but negative in the second quadrant. It's negative in the, or it's positive in the second quadrant, and then negative in the fourth quadrant. So we should expect this to change things if we were to say 1 minus the sine of theta plus pi. It's going to produce the negative version of the output. So we can already expect this would be 1 plus the sine of theta. But we can also expand this out in the same way we did here, and you should get the same result. So if you want to double check. This would also be symmetric if we had an r squared. Then if we plug in negative r, it will basically delete the negative. So that's kind of the things to watch out for. An r squared, or maybe some trig function that has symmetry across the origin. So maybe something with the tangent. So now we know we should expect the graph at least to be symmetric across the y-axis. So that means if we find points using angles from negative pi over 2 to positive pi over 2, say we get some points here, try to figure out what the curve would look like, we get a bunch of other points for free just by reflecting across the y-axis. So that will help to make graphing a bit easier. So let's get those points together. Let me create a table here. So let's remember that r is equal to 1 minus the sine of theta. So let's start at negative pi over 2. Well, that would be 1 minus the sine of negative pi over 2 is negative 1. So 1 plus 1, that will equal 2. So we should have the point 2 comma negative pi over 2 in terms of r theta points. So let's just build up a bunch of points and then we'll start to plot them on here. So let's take negative pi over 3. That would give us 1 minus negative root 3 over 2, which we'll need to do some decimal rounding here, but that's approximately 1.87. Then we can try negative pi over 6. So that will give us 1 minus negative 1/2. So 1 plus 1/2, that's 1.5, 1.5. All right, and how about 0? So I'm just picking points, or picking angles from negative pi over 2 to pi over 2. So yeah, we can choose 0. That's 1 minus the sine of 0. Sine of 0 is 0, so we get positive 1. For positive pi over 6, 1 minus the sine of pi over 6, which is 1/2. So 1 minus 1/2 is 1/2, 0.5. And we can say pi over 3. That's 1 minus the sine of pi over 3, so 1 minus root 3 over 2. That'll give you approximately 0.13. And then for pi over 2, this is 1 minus the sine of pi over 2, which is 1. So that's equal to 0. So let's plot these points and then use symmetry to get some additional points. So we should have the point 2, negative pi over 2. So I would imagine going out to the circle of radius 2 and then going down to negative pi over 2, rotating clockwise because the angle is negative. So we should start at this point. Then it would go to negative pi, 1.87, negative pi over 3. It's 1.8, something kind of close to 2, and down to negative pi over 3. So maybe something like this. But we know we're symmetric across the y-axis, so we should also have another point over here. We can get that one for free. Then we have 1.5, negative pi over 6. So 1.5, negative pi over 6 should place us here. And then again, we also will get a free point on the other side. Then 1, 0. So radius of 1, angle of 0. So something like that. Get another one on the other side. Then 0.5 pi over 6. So right there. Another one on the other side. Then 0.13 pi over 3. So very close. This graph is a little bit weird. It's not exactly, you see how the lines are kind of not exactly crossing at the center, so a little bit strange. And then the point 0 pi over 2. So we have our traces of points. Let's connect it with a smooth curve, because this is a smooth equation. Notice what we get. Oops. Let's do that again. So it looks like a heart. It has this sort of sharp indentation on the top. It doesn't have a point on the bottom, kind of exacerbating it a little bit because I really want it to have a heart shape, but we get essentially, it's more smooth on the bottom, but we get a heart shape. So this kind of shape is called a cardioid. So that is a reference to the heart. Think of like the term cardio. It's about like a heart workout. So we get some kind of heart shape. And we'll see that generally with equations that will look like this in polar form. So we're going to use this general strategy of plotting points and taking advantage of symmetry to get a few more interesting shapes here. So we get a cardioid when we have something like this. You have some value plus or minus a sine or cosine. And so I would recommend maybe playing around on Desmos or some kind of graphing utility and just try different variations. Try it with the sine, try it with the cosine. You'll see that depending on the trig function, you'll get a certain orientation, like facing left or right, facing up or down, and maybe some transformations. So it's helpful to just play around and try to see if you can pick up on some patterns in the equation that will help you to easily identify some of these graphs. All right, so let's keep going. Let's look at number 8. So now we have r equals 3 plus 2 times the cosine of theta. So this will look a little bit different from our last one. But let's take the same approach. Let's check for polar axis symmetry. I'll just say x-axis. So that's where we replace theta with negative theta. So 3 plus 2 times the cosine of negative theta. Well, we should recall from even odd properties of the cosine that it'll essentially just delete the negative. because the cosine of a positive angle is the same as the cosine of the negative angle. Think about it that way. So this will have symmetry across the polar axis, across the x-axis. For y-axis symmetry, this is where we would replace theta with pi minus theta. So we can expand this using angle subtraction for the cosine, but also we could use the argument that pi minus theta is the similar angle in the, say like the second quadrant if we have some angle in the first quadrant. And that produces a negative cosine, or it's opposite in sign, in SIGN sign. So we should expect that this would give you a negative in front of the cosine. So that will make this 3 minus 2 cosine theta, which is not the same. But you can prove it to yourself by expanding this with angle subtraction for the cosine. So this will not have y-axis symmetry. And then for origin symmetry, we don't have r squared, so that won't work. And then if we replace theta with theta plus pi, we're basically just saying go across the unit circle. And yeah, that will produce the opposite value of the cosine. We would get that same result as we did for our test for y-axis symmetry. This would be 3 minus 2 cosine of theta. So we only have symmetry across the x-axis. So let's produce some points. If we have symmetry across the x-axis, that means we should choose points, or we should choose angles between 0 and pi. And then whatever we get, we can just reflect across and get some additional free points. So let's build another table. And I'll choose angles from 0 to pi. Let's remember that r is equal to 3 plus 2 cosine of theta. So let's start with 0. That means r would be 3 plus 2 times the cosine of 0, which is 1. So 3 plus 2 is 5. Then pi over 6. This will be 3 plus 2 times the cosine of pi over 6, which is root 3 over 2. This will be approximately equal to 4.73. For pi over 3, this will be 3 plus 2 times the cosine of pi over 3, which is 1/2. So 3 plus 1 will be equal to 4. Then for pi over 2, 3 plus 2 times the cosine of pi over 2, which is 0. So 3 plus 0 is 3. Then we can use 2 pi over 3. So 3 plus 2 times the cosine of 2 pi over 3, which is negative 1/2. So 3 minus 1 is 2. And we can do 5 pi over 6. So 3 plus 2 times the cosine of 5 pi over 6, which is negative root 3 over 2. So that is approximately 1.27. And then for pi, 3 plus 2 times the cosine of pi, which is negative 1, get positive 1. So let's plot these and then use some symmetry. Our first one would be the point 5, 0. So don't have a ring for 5, it's about right there. And we're on the x-axis, so we don't get a symmetrical point. Then we have 4.73 and pi over 6. So 4.73 pi over 6 would be something like that. Making a little estimate, and then we would get a reflected point on the other side. Then 4 pi over 3. So now we're here. We get reflected point on the other side. Then 3 pi over 2. So radius 3, angle of pi over 2. So 1 there, 1 on the bottom. Then 2 pi over 3. So something there. Then a reflected point would be down here. Then 1.27. So like 1 1/3 about, and 5 pi over 6. So something like this, the reflected point, and then pi 1. And then let's connect this with another smooth curve. So it looks somewhat similar to the cardioid, but you don't get a sharp angle. Oops, you don't get a sharp angle like at the top of the heart. It's more of a, I think I've heard it called like a dimple, like a, just a little indentation. So we're getting these weird kind of like augmented circular style shapes. So what did they call this? So they call this a limacon, which is French for snail, I'm pretty sure. Let me make sure. Let me double check. Yeah. Or is it Latin? It definitely means snail. Do you see a snail? I'm not sure. And it says without an inner loop. So we'll see a version that does have an inner loop. We'll see what they mean by that. So like a kind of like a dimpled circle. So they give us our formal definition here. So they don't have an inner loop. It looks like two different terms, a plus b cosine, or a plus b sine, or a minus b cosine. Notice a and b are different. It says a is greater than b. So that's a little bit different from what we had previously with our heart, our cardioid. Notice if we were to distribute this a in the formula, it would be the same value, like a plus a cosine theta. In our case, it was 1, like 1 plus 1, where we had 1 minus 1 sine of theta. It's like the same value. So some subtleties here. But you can see how they produce slightly different shapes. We have this sharp heart shape and this more like dimpled circle. All right, let's see an example of one with an inner loop. So I think this is characterized where this value next to the trig function is greater than the other value. And we have the cosine. So that means we should expect similar symmetry across the x-axis. You can learn to already kind of pick these up as you look at them. But yeah, if we were to replace theta with negative theta, we know the cosine like absorbs it basically. We get the same function back, so we have x-axis symmetry. Y-axis symmetry, if we replace theta with pi minus theta, we'll get an opposite cosine value, or we can expand that out and prove it to ourselves, but we'll get not the same function back, so no y-axis symmetry. And we don't have an r squared, and it doesn't have y-axis symmetry, so it shouldn't have origin symmetry either. I already expect it not to have that, but the technical test would be 1 plus 2 times the cosine of theta plus pi, If you expand that out, you'll get a negative cosine. So it will produce 1 minus 2 cosine theta. So same situation as last time. So let's use those same angles from 0 to pi. So this time r is equal to 1 plus 2 cosine of theta. So plugging in 0, we get 1 plus 2 times the cosine of 0, which is 1, so positive 3. Plugging in pi over 6, we get 1 plus 2 times the cosine of pi over 6, which is root 3 over 2. This is approximately 2.73. Then pi over 3, 1 plus 2 times the cosine of pi over 3, which is 1 half. So 1 plus 1 equal to 2. Then pi over 2, 1 plus 2 times the cosine of pi over 2, which is 0, get positive 1. 2 pi over 3, we get 1 plus 2 times negative 1 half, which will give us 0. 5 pi over 6, get 1 plus 2 times the cosine of 5 pi over 6, which is negative root 3 over 2. So approximately negative 0.73. So notice we're seeing a negative r value. And then pi, 1 plus 2 times negative 1. So 1 minus 2, we get a negative 1. So let's see how these negative r values will affect our output here. So our first point is 3, 0. We'll have a nice point here. Then pi over 6, 2.73. So roughly here, and we'll get a symmetrical point across the x-axis. Then pi over 3, 2. And another symmetrical point. Oops. Should actually be down here. Then pi over 2, 1. So a point here, another point down here. Then 2 pi over 3, 0. So we get 0 point. Then 5 pi over 6, negative 0.73. So 5 pi over 6 is over here. And then negative 0.73 would put the point like somewhere here. And we will also get a symmetric point across the x-axis. And then pi negative 1. So this would be pi positive 1. The negative 1 will place it over here. And I think this point should be more here. So let's try to trace this out. We start at 3, 0. Then continue. So we're getting our curve. Let me try to make this a little bit nicer. And then notice we're going to produce this inner loop. And then it curves back out. If we keep increasing the angles, we'll get all of those points that we got via symmetry. And so there is a sort of an aspect of this, of the order as the angle evolves, how is the curve traced out. Like we can imagine putting little arrows saying that the curve is being traced in that direction. So this gives us our snail, our limestone, with an inner loop. The inner loop is regarding this inner little loopy circle. So in general, our limestone with an inner loop. Notice the condition here. It's saying when b is greater than a. So when the number that's in front of your trig function is greater than the other number. When a was greater than b, we didn't get the inner loop, we just got that like dimple shape. All right, our next set are called rose curves, which I enjoy these a lot. These are pretty fun. So let's go through the same process. Now we have r equals 2 times the cosine of 2 theta. So let's check our x-axis symmetry. We're dealing with the cosine, so we should expect that if we replace theta with negative theta, we're producing the negative of the angle, which will give us the same cosine value. And again, we can get that by expanding this in some way. Maybe use the angle addition for the cosine, or one of the double angles. For y-axis symmetry, in this case, we're replacing theta with pi minus theta. So multiplying that through, that means r equals 2 times the cosine of 2 pi minus 2 theta. This one's a bit less obvious to imagine. So let's actually expand this out and see what we get. So this should be equal to 2. Now the cosine of 2 pi minus 2 theta, that should be the cosine of 2 pi times the cosine of 2 theta plus the sine of 2 pi times the sine of 2 theta. So that will be 2. The cosine of 2 pi is 0, so that deletes that first term. Or no, I'm sorry, the cosine of 2 pi is positive 1, so that will keep that first term. So we get the cosine of 2 theta. And then the sine of 2 pi is what is equal to 0, so that second term will just become 0. So we get 2 times the cosine of 2 theta, which was our original function. So we have symmetry across the x and the y-axis. That means by definition we have origin symmetry as well. So we can just already say yes to that one. So that means we can test even less points. If we just test points from 0 to pi over 2, then we get a symmetrical point across both the x and the y-axis and across the origin. So that will be extremely useful. So let's pick some angles between 0 and pi over 2. And then this time r equals 2 times the cosine of theta. Make that look a little nicer. So let's start with 0. This would be 2 times, oh, and this is 2 times the cosine of 2 theta. So 2 times the cosine of 2 times 0 is the cosine of 0, which is 1. So we get 2. Then for pi over 6, 2 times the pi over 6 is pi over 3. So the cosine of pi over 3 is 1/2. So 2 times 1/2 is positive 1. Then pi over 4. Pi over 4 times 2 is pi over 2. So really this is 2 times the cosine of pi over 2, which is 0. So we get 0 here. Then pi over 3. 2 times that would be 2 pi over 3. So 2 times the cosine of 2 pi over 3, which is negative 1/2. That'll be -1. And then pi over 2, 2 times that is pi. So 2 times the cosine of pi, which is -1. So we get -2. So let's see what this will trace. So we have the point 2, 0. We got a point here. Then pi over 6, 1. But now let's use symmetry. So we should have another point over here and another point below and another point across. Then pi over 4, 0. So we end up with a point at the center. Then pi over 3, -1. So pi over 3 and then a -1 will place it down here. Then we would get symmetrical points. And then pi over 2, -2. Or -2 pi over 2. So that would give us a point down here, but also a symmetrical point. And then we also should have a symmetrical point over here from our original point. Got to add that one. So what do we get here? If we traced out this curve, it might be more helpful to list out more of these points explicitly to get an idea of how it's traced. But we start at this tip, and then change to purple. So we got these points, then it traced it out in this direction. And if we were to continue this, we would see another curve like this. So we get kind of like a half circle. And we get another point. It's like another half circle. And another set of points. And we complete it with this nice rose curve. So I think this is a really interesting shape. It's like this series of half circles that end up producing this flower-like geometric shape. Yeah, very interesting. So we can also have more variations of this if it involves the sine, and then also if we have some other number multiplied inside of here. But that's the basic structure. So let's take a look here. The rose curve. So it looks like some number times the sine or cosine with some number n multiplied inside. So it says if n is even, I'll use a different color here. They specify that n is not equal to 0. But if n is even, then the rose has 2 times n petals. So we saw that here, n was even, and our n value is 2, and we saw 4 petals here. And then it says if n is odd, then it has n petals. So if this had like a 3, we would see a curve that has 3 petals on it. So again, it's useful to look at maybe Desmos or something and play around with this to get some different examples and see like how different values will produce different shapes. All right, our next example has an r² value. So we're given r² equals 4 times the sine of 2 theta. So we get what looks kind of like a rose curve, but we have this squared r. Oops, and I left it already filled out here, so kind of spoiled the surprise, but let's reproduce this graph. Um, we should already see this is going to have origin symmetry. One of the tests for that was to replace r with negative r. Well, if we square negative r, we'll just get r back. Or we'll get like r squared back. So it's symmetric about the origin, meaning we have both x and y axis symmetry. So let's use those same values. Let's do this in like 3 steps this time. So we'll have our angle. Then r, if we weren't squaring r, well, if we do 4 times the sine of 2 theta, that would give us r squared, and then we'll need our r value. So we'll take the square root after we find out what 4 sine of 2 theta is, because that will give us r squared, but we want r and theta to plot our points. So we plug in 0. This is 4 times the sine of 0, which is 0. The square root of 0 is 0. For pi over 6, 4 times the sine of pi over 3, because we're multiplying this by 2. So root 3 over 2. So that'll give us 2 root 3. And if we take the square root of that, you get approximately, we get plus or minus 1.9. Because we're technically taking the square root of both sides of an equation. And that's what's producing our symmetry here, this positive or negative. Then we can have pi over 4. So we get 4 times the sine of pi over 4 times 2, so that's pi over 2. Sine of pi over 2 is 1. So we get 4, take the square root, plus or minus 2. And pi over 3, we get 4 times the sine of 2 pi over 3, which will give us root 3 over 2, positive root 3 over 2. So another 2 root 3, so we'll get another plus or minus 1.9. And then for pi over 2, that'll become 4 times the sine of pi, because we're multiplying pi over 2 by 2. Sine of pi is 0, so we get 0. So let's plot these and use our symmetry. Get the point 0, 0. Then 1.9 pi over 6. So 1.9 is like way up here, but we also get the negative as well. Then pi over 4 and 2, we also get the negative. Then another 1.9 with pi over 3, we also get the negative, and back at 0. So tracing this out, we get this, it looks like an infinity symbol. So very nice. We get a lot of really interesting shapes in polar graphs. Things that are, and this is arguably a pretty simple formula, although it's taking some time for us to work it out to, it's maybe less intuitive to look at it and see what kind of shape it's going to make. But we're able to produce these really nice curving, looping patterns using these equations. Another really big benefit is that this is like if we look at our rose curve, this is a function. We do produce functions, like with our circles as well. In the, that was like in our last section. But in terms of xy coordinates, x squared plus y squared equals 9, we use the vertical line test because this is producing multiple y values for our x value input. But in terms of the in terms of the polar graph, sorry, I'm like jumping all over the place. In terms of a polar equation, we can have, like, we don't get that same function breaking behavior where a single input produces multiple outputs, or there's multiple outputs tied to a single input. We don't have that problem in polar coordinates. We have r as a function of theta. So some other benefits to graphs in the polar form. Let's catch back up here. So let's look at one more. And I already have the table produced here. So let's see what this will produce. So this one looks very interesting. It's saying r equals e to the power of theta divided by 5. Strange looking object. So what do we get? They start with the angle negative 3 pi over 2. So that would be 3 pi over 2 is over here. So negative 3 pi over 2 would be coterminal with pi over 2. And then we have the r value of 0.39. So something like that. Then negative pi, 0.53. Well, negative pi is coterminal with pi, so we get something like that. Then negative pi over 2, 0.73, so down here. Negative pi over 4, 0.85. Maybe I should move this one a little bit lower. Then 0, 1, or I'm kind of reading this backwards. Should be r theta, so 1, 0. Then 1.17 pi over 4. 1.37 pi over 2. Pi 1.87. 3 pi over 2, 2.57. So something like that. 2 pi 3.51. And on from there. So check out this pattern. We started here. And we get a really nice, beautiful spiral shape. Let me make this look a little bit better. I don't know if I did much better there. Let me give it one more try. So hard to imagine how we can produce the equation of a spiral in rectangular coordinates. This is a very complicated pattern. But in terms of polar coordinates, it's actually quite simple. The simplest version of this would just be r equals theta. As theta increases, r will also increase. So we can imagine just spinning outwards. We can start with the angle of 0, so it would have an r value of 0. But as we start to rotate, then r would get larger. So we can imagine continuing to rotate, r will continue to get bigger, and we get a larger and larger spiral outward. So super simple polar equation. This one's a little bit more complex, but because theta is being manipulated by being divided by 5 and then put as an exponent of e. But we get a similar kind of effect, the spiraling effect. So this was like a bonus one. But yeah, if you're using functions to model behavior, think about when it would be useful to have a spiral. Or maybe some kind of loop, some kind of curving cycle. What kind of things might behave in this way? Very interesting. So the text gives you some nice summary boxes, and if we have class in person, I'm going to pass this out as a handout, but it covers basically what we've gone through equations of lines in polar form, equations of circles. We saw a few different cases there. Then in other equations, we have the cardioid, which has this like sharp point, so the heart shape, the limacone without an inner loop, more like a dimple. Then with the inner loop, we get this curve inside. Then we have our infinity symbol. Not entirely sure how that's pronounced. Lemniscate, I think. Then a rose petal with even or odd number of petals. So it's worth looking through this, and again, I would recommend maybe in Desmos and polar settings, just play around with variations of these equations and see what kind of interesting shapes you can produce. I'm particularly fond of these rose curves. It's just so interesting to me. All right, that completes our section on graphing polar equations. So we did some conversion to rectangular equations, and that was useful for lines and circles. But then we use this method of plotting points with and then using symmetry. This third section, we didn't have a specific example. It says, oh no, I'm sorry. We tested polar equations and then graphed by plotting points. There was another example in the text that was called like plotting polar equations quickly. And it's basically using these techniques and also looking ahead already, like trying to identify what kind of shape we should expect to see using these general patterns. So based on what the equation looks like, oh, we might expect a cardioid shape. It will have a certain symmetry. You can choose a few points and then get the graph from there. All right, that'll be it for this section and this video, and I'll see you next time.